Okay, welcome to the first video of probability series. And uh, today, in this video, I will talk about event and probability. And the first definition is about the sigma field, or we can call it sigma algebra. So why we need to talk about or study about sigma algebra? So, as you studied already in high school, in bachelor or in master about probability, you will see about the probability space that we denoted by omega fp. It's just a notation. Maybe the notation can be different in different textbook or yes or something. But I just want to show you that when we talk about probability, we start from a random experiment that the outcome can be anything. So the first item, omega, it is the set of all possible outcome. For example, an experiment about flip a coin, that the coin has two faces, a head and tail. It's just a simple example. And when we flip a coin one time, then the result can be head or can be tail. So in this case, the set omega of all the possible outcome, or we call it sample space, is equal to head and tail. It means that it contains all the element of outcome. So after we know about all possible outcome that may happen already, so the next step we want to measure what is the probability, what is the possibility that one element or many elements in this set happen in this the result may happen. For example, if you are interested in head, so you want to know that what is the possibility, what is the probability that head may happen in this experiment. So that's why we need a measure to do it. We need a measure to measure the probability, the possibility of it. So that's why in this three element in this space, we have P, which is a probability measure. And the next video, I will tell you about what is the probability measure. And in mathematics, when we talk about measure, when we have a measure, we have to know that the measure have to put on the measure set, the measurable set. So in this case, we need a measurable set which is denoted by F. So F, it is the sigma algebra or sigma field that is a measurable set, and we can put the probability measure P on it. So if we have a set, how can we know that this set is a sigma field or sigma algebra of the sample space omega? So the definition 1.1 will tell us about it. So start from omega. Let omega be a non-empty set. We have to make sure that our sample space is not empty. So a sigma field F on omega is a family of subset of omega such that it means that F, it is a sigma field on omega. It has to satisfy these three conditions. So the first condition is that the empty set have to belong to F. We have to make sure that the empty set is F is contain empty set. The second condition is about the complement. It means if we have a set A which is belong to F, then complement of A that is equal to omega minus A is also belong to F. This is the second condition. And the third condition is about the union of subset. So if we have sequence, if we have A1, A2, the set A1, A2, and so on, it's a sequence of set in the set in F. Then if they are union, it means that A1 union with A2 union with so on also belong to F. In this case, if the set F, if the if the set F satisfy these three conditions, we call F is the sigma algebra or sigma field on omega. Okay, now let's start with some example. The first example is if I have a set F0 which is have two elements, empty set and omega, where omega which is a non-empty set. So we want to know that F0 is F0 is a sigma field on omega or not. Okay, let's say omega equal to h and t. H and t, head and tail. So we want to know that F0 is a sigma field on omega or not. We have to check these three conditions. For the first condition is we have to check if we belong to F or not. Oh, sorry, empty set belong to F or not. And in this case, obviously, we can see that the empty set is belong to F0. Okay, so the first condition is satisfied. The second condition is about the complement of all the elements in the set F0. So since F0 here we have only two elements, empty set and omega. So let's check about the complement of these two elements. The first one is the complement of empty set. I think we know already that the complement of empty set is equal to omega. Why? Why is that? Because, like, if A belong to F, let's see the second condition. If A belong to F, then so that's the complement omega minus A. So the complement of empty set is equal to omega minus empty set, which is an empty set. An empty set it belong to F. F0. And another element is complement of omega. Complement of omega is equal to omega minus omega, which is an empty set. And this one is belong to F0. So we see that the set F0 is satisfy the set F0 satisfy the second condition. Now we go to the third condition about uh, the union of the sequence of all subset of F. So since our F0 here we have only two elements, so the union of these two elements, I mean that empty set union with omega. And obviously we see that empty set union with any set is equal to that set, I mean that is equal to omega, which is belong to F0. So we see that F0 satisfy all three conditions of sigma field. That's why we can say that F0 is a sigma field or sigma algebra on omega. Okay. Uh, Now let's go to the second example. Second example is also about the same experiment as the first example is flipping a coin, but in this case, I will talk about the power set of omega. So if we still have omega, which is equal to h and t, then the power set of omega that we denoted by 2 to the power omega, or for the sake of simplicity, I denote it by f1, is equal to, we know about power sets already, empty set, h, t, and omega itself. And we want to see that if the power set of omega is a sigma field on omega or not. So we have to check both three conditions. The first condition is about the empty set. We have to check that the set F1 is contain the set F1 contain the empty set or not. And obviously empty set is an element of F1. So the first condition is satisfied. Now we go to the second condition about complement of all the elements in F1. So for the first element, empty set and omega, I don't want to talk anymore because we can see in the first example. I will check about h and t. If the complement of h and t is still belong to the set F1. So the complement of the set H is equal to omega minus H. So omega minus H is equal to T because our omega is equal to H and T. So the set T, and it is an element of F1. Similarly, complement of the set T is equal to omega minus H. Oh, sorry, minus T, which is equal to H, and this one also belong to F1. So the second condition is fulfilled because yes, there are 4 elements in F1, but for empty set and omega, it's trivial to see. So now we go to the third condition. The third condition is about the union of the element of all the element in F1. So it is not hard to see if we union all the element in F1, it also belong to S1. For example, when we union empty set with H, it will be equal to H and it is belong to F1. Okay, for example, 2 union. It is equal to 8. Okay, belong to F1. And because empty set union with other non-empty set will be equal to the non-empty set. So when we take empty set union with T and with omega, it still be the set T and omega and also belong to F1. So I won't take empty set anymore. So I won't talk about empty set anymore. But now go to this pair union with T is equal to H T. And this is omega, which is equal to which is belong to F1. And when we take H and T, to be union of to be union with omega, it will be equal to omega because the set H, it is the subset of omega. So when we union it, it equal to omega. So this one is also belong to F1. So we can see that uh, if we union all, I mean, if we union all possible element, all the element in F1, it still belong to F1. So the third condition is satisfied. So we can say that the power set of omega is a sigma algebra or sigma field. Therefore, 2 to the power omega, or I denote it by F1 is a sigma field on omega. Okay. The first example, we call it a trivial, a smallest sigma field on omega because it contains only two elements, omega and empty set. And the second example, it is the biggest sigma algebra, sigma field on omega because it is the power set that which is a set that contain all the subset of omega. So it is the biggest sigma algebra. Okay, now let's go to another example that uh, omega is still h and t, and f2 here, for example, the element is empty set and omega and h. F2 is a sigma field on omega or not. So let's check the three conditions. So the first condition about empty set is okay. Okay, because empty set is belong to F2. But the second condition about the complement is not satisfied. Is not satisfied. Why I said like this? Because if we choose the set H, the complement of H, which is equal to omega minus H and equal to T. And this one is not belong to F2. So F2 is not a sigma field on omega because it's not satisfied the second condition. Okay, I think that's enough for the first video, and the next video I will show you about the probability measure that I denoted by P in the previous time. So okay, see you in the next video.